Once thought to evolve along a predictable trajectory originating from the Big Bang, the universe now reveals complexities that could fundamentally reshape modern cosmological theories. With the powerful James Webb Space Telescope, JWST, probing the farthest reaches of the cosmos, scientists are encountering massive, mature galaxies that challenge long-standing models. Unexpected variations in what we call dark energy, along with hints that time itself might not flow uniformly across space, are forcing a reconsideration of the universe's very fabric. A central figure in these revelations is dark energy, a mysterious force named more from our lack of understanding than insight. It was originally identified when researchers observed that galaxies are not slowing down due to gravity, as once assumed, but instead are accelerating away from each other. This astonishing discovery implied the presence of a previously unknown energy exerting a repulsive force on the cosmos, an idea that Einstein had accounted for in his equations of general relativity through the concept of the cosmological constant. In simplified terms, this force is modeled as a uniform energy density that fills space. According to this framework, dark energy constitutes about 68% of the universe. 27% is made up of dark matter that invisibly holds galaxies together, and just 5% consists of ordinary matter, everything from stars and planets to life itself. The first clues to the universe's accelerating expansion came from studying distant supernovae, whose light patterns indicated a faster rate of cosmic growth over time. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, later confirmed these findings. However, recent high-precision measurements from advanced telescopes and massive sky surveys are introducing inconsistencies. These new data sets suggest that dark energy may not be constant after all. It could vary in strength over different epochs or behave differently depending on the region of space. A major debate emerging from this is known as the Hubble tension, a discrepancy between two distinct methods of calculating the universe's expansion rate. One method relies on the early universe's light patterns, the cosmic microwave background, while the other is based on direct observations of nearby galaxies and supernovae. If dark energy were truly uniform, both calculations should agree. But they don't. This mismatch has led to bold hypotheses. Perhaps dark energy evolves over time, or maybe our current cosmological model is missing crucial elements. One particularly provocative idea involves the flow of time itself. The time-cape cosmology model proposes that time may move at different speeds depending on the gravitational environment. If time flows faster in the vast, empty voids of space than in denser galaxy clusters, it could create an illusion of accelerated expansion, mimicking the effects attributed to dark energy. This wouldn't rule out dark energy entirely, but would challenge how we interpret key astronomical data. Other researchers are investigating whether dark energy stems from quantum fluctuations in empty space or is linked to hypothetical dynamic energy fields, like quintessence, which change over time and space. These theories open the door to vast, largely unexplored areas of physics that still lack definitive observational proof. The JWST, with its ability to observe the earliest stages of cosmic evolution, offers an invaluable tool for testing these ideas. By examining how galaxies form and how space expanded during different cosmic periods, astronomers can assess whether dark energy has remained constant. If galaxy clusters appear at unexpected rates, it could indicate that dark energy's influence has shifted over time. Despite all these insights, dark energy remains one of the deepest mysteries in astrophysics. Solving it may ultimately require us to revise not just our theories, but our understanding of time, space, and the very nature of reality itself. As instruments like the James Webb Space Telescope, JWST, continue to gather increasingly precise data, our understanding of the universe, and particularly the nature of dark energy, faces growing challenges. To make sense of the mounting contradictions, scientists may need to revise Einstein's widely accepted equations or introduce new physical principles. One such alternative framework is timescape cosmology, which offers a radical reinterpretation of cosmic acceleration. Rather than invoking mysterious energy forms, timescape cosmology suggests that the perceived acceleration of the universe could stem from misinterpreting the nature of time itself. According to this theory, time flows differently in regions with varying matter densities, such as dense galaxy clusters versus vast cosmic voids. These differences may distort observational data, making it appear as though distant galaxies are accelerating away from us, when in fact, this illusion could result from uneven time flow across the cosmos. This challenges a conventional assumption that the universe shares a single, synchronized cosmic clock. Traditional cosmology treats time as progressing uniformly and dates the universe to approximately 13.8 billion years. Timescape cosmology, however, argues that even slight variations in time flow, when compounded over billions of years, can lead to significant discrepancies in our observations. Proponents of the theory believe it may help resolve the so-called Hubble tension, the discrepancy between different measurements of the universe's expansion rate, and offer an alternative explanation that doesn't rely on a constant dark energy term. In this view, the appearance of cosmic acceleration arises not from an unknown force, but from the irregular curvature of space-time caused by the non-uniform distribution of matter. Ongoing studies are testing timescape cosmology against large-scale cosmic datasets to assess its predictive power. Some early results suggest it can match, or even slightly outperform, the standard model in certain cases. Still, the theory remains on the fringe due to its mathematical complexity and the lack of widespread acceptance among mainstream astrophysicists. Critics caution against abandoning simpler models prematurely, noting that dark energy might not be constant. It could evolve over time, or that general relativity may need refinement to better match observational data. This is not about disproving Einstein, but about evolving our models to reflect a possibly more intricate universe than we currently understand. One key assumption in standard cosmology is that, on a large scale, matter is evenly distributed and the universe looks the same in every direction, isotropy. Timescape cosmology challenges this, suggesting that such simplifications may hide subtle yet impactful variations. New JWST findings could put this theory to the test. If early galaxies appear to evolve for their age or display unexpected structures inconsistent with current dark energy models, timescape cosmology might gain traction. For instance, JWST has already delivered astonishing visual and spectral data from near the dawn of the universe, capturing light emitted more than 13 billion years ago. Contrary to expectations of small, irregular early galaxies, it has revealed massive, well-organized systems with mature features. A striking example is the so-called Big Wheel Galaxy, a disk-shaped formation with notable symmetry that defies conventional timelines of galaxy formation. According to standard theory, such complexity should take much longer to develop, raising important questions. Is our cosmological clock off? Or could galaxies have formed far more efficiently than we thought? These questions are crucial because the structure and distribution of early galaxies shape our understanding of fundamental cosmic phenomena, such as the role of dark matter, the nature of dark energy, and the dynamics of cosmic inflation. If galaxies in the early universe were larger and more evolved than expected, it could mean the universe is older than currently believed, or that the processes of galaxy assembly operated at unexpectedly rapid speeds. Ultimately, timescape cosmology is part of a broader set of non-traditional theories aiming to reinterpret cosmic expansion. As the JWST continues to revolutionize our view of the early universe, it may either reinforce the current paradigm or catalyze a profound shift in how we understand space, time, and the cosmos itself. The discovery of heavy elements in ancient galaxies, a cosmic puzzle. The James Webb Space Telescope, JWST, has detected heavy elements in some of the universe's earliest galaxies, deepening existing cosmic mysteries. Elements heavier than hydrogen and helium are typically forged inside stars and spread through space during supernova explosions. The presence of such elements in ancient galaxies suggests that cycles of stellar birth and death occurred far earlier and perhaps more rapidly than previously believed. This points to an accelerated pace of cosmic evolution in the universe's infancy. JWST's ability to observe ancient light also intersects with how we measure the universe's expansion rate. If new observations don't align with projections based on early cosmic light, it may indicate that dark energy, or some other fundamental property of the universe, changes over time. However, some anomalies might stem from observational artifacts. For instance, extremely bright distant objects could be misidentified as closer objects with unusually red light. To reduce such errors, astronomers rely on multi-spectrum cross-verification, using ground-based instruments. Still, the consistent detection of massive early galaxies is too frequent to dismiss as mere observational error. This has energized the scientific community and sparked serious discussions about whether the Big Bang model, though still widely supported by evidence such as the cosmic microwave background, may need revision or refinement. The unexpectedly mature galaxies seen by JWST are challenging existing models of galactic evolution. One explanation posits that the universe's first stars, known as population 3 stars, were extremely massive and short-lived. These stars could have rapidly enriched interstellar gas with heavy elements, triggering further star formation. Others suggest that current simulations of galaxy formation, which rely on cold dark matter and hierarchical merging, might underestimate the speed or scale of early structure development. Although some scientists entertain the possibility of distance miscalculations, such errors are unlikely to account for all the anomalies observed. The prevalence of large galaxies in the early universe also raises questions about the formation of supermassive black holes. Traditionally believed to form over long periods, these massive objects appear to have emerged much sooner than expected, posing yet another challenge to conventional cosmology. These findings strain current simulations and assumptions, prompting the development of more dynamic and robust computational models. At the core of these complexities is a provocative possibility. Perhaps our understanding of time and space itself is incomplete. Cosmic voids, vast, underpopulated regions of space, are gaining attention for their potential to influence cosmic evolution. According to timescape cosmology, these voids could experience time differently than denser regions due to gravitational time dilation. Over time, this disparity might create observational effects that mimic an accelerating universe. Although voids are not truly empty, containing faint galaxies and filaments of matter, their relative emptiness could cause phenomena within them to appear more evolved than those in denser regions. Studies of gravitational lensing, where massive objects bend the path of light, may offer crucial insights into these potential temporal distortions. So far, the data is intriguing but not definitive. The revelations from JWST and similar missions may mark the start of a paradigm shift, one that could alter how we understand not just galactic evolution or dark energy, but the nature of time itself. These are not science fiction musings. They're grounded in Einstein's theory of relativity, which established that time is not absolute and that gravity warps both space and time. While skeptics advocate for more conventional explanations, like faster early star formation or misestimated cosmic density, proponents of timescape cosmology argue that time-based variations might offer a simpler, more unified framework without invoking mysterious dark forces. Regardless of which theories prevail, these ideas are compelling scientists to think more broadly. Mapping the distribution of matter and the intricate links within the cosmic web will sharpen our understanding of the universe's structure. Upcoming instruments, with expanded scopes and finer resolution, promise to clarify how voids, galaxy clusters, and the flow of time are intertwined. One especially fascinating development is the apparent alignment of galaxy spins. In a universe born from random quantum fluctuations, one would expect galactic rotations to be randomly distributed. Yet large-scale surveys suggest a statistically significant number of galaxies may be spinning in similar directions. This surprising trend recalls earlier observations of the cosmic microwave background, where mysterious alignments, nicknamed the axis of evil, challenge the notion of a directionless, isotropic universe.